talk. This is going to talk about, we're going to talk about self-resonant conflicts.
Good afternoon, ladies and gentlemen. My name is Tetsuya Asano. I'm a student in Professor Madhukar's group. And thank you very much to give me this nice opportunity to give an oral presentation in this research symposium. Probably your stomach is waiting for the lunch. Just let me get on my contents. First of all, given the divergent background of the audience in this symposium, let me start with a brief introduction of the field of my study, which is self-assembled quantum dots and quantum dot infrared photodetectors. For growth of the semiconductor heterostructures, when the gross material, the Lattice constant of the gross material is larger than the substrate material, the strain will be accumulated as growth will proceed, and eventually the strain will be relaxed at some critical thickness. When the lattice mismatch is as small as about 2%, the growth mode is layer by layer growth, and the strain relaxation will be done by the formation of the dislocation. On the other hand, when the lattice mismatch is between 2% to 7%, the coherent 3D island is formed. 3D coherent island is formed with this wetting layer in the early stage of the growth. And this island is expanding outwards to relax its strain. And this is the TM image of this coherent quantum dot, and here is the AFM image of the island. And since these islands are coherent, you can use it for the optoelectronic devices. And also, if you see these scales, the vertical scale of quantum dot is 10 nanometer or less, and the lateral size is about 20 nanometer. So the electron is can be three-dimensionally confined. And to utilize this three-dimensional confinement of the quantum dot, also you need to cap it by the coherence. You need to cap it coherently. So here is the TM structure of the indium arsenide quantum dot capped with gallium arsenide, and the structure is repeated by 5 times. And the coherent island and also the electron confinement is manifested by this strong photoluminescence intensity as a function of these various number of layers. And more detailed investigation of the energy levels by making the more detailed investigation of the energy levels, which is you can evaluate the separation between these discrete energy levels. Here is the schematic diagram for the indium arsenide quantum dots capped with gallium arsenide, and these values are kind of typical values, and that can be tuned by choosing the right material or thickness of the quantum dot and capping layers. And if you see this intraband transition, the range of energy is about 50 millieV to the 300 millieV at maximum. And these energies coincide with two important infrared wavelength regime, which has an atmospheric window. One is mid-wave IR, around 3 to 5 micron, and the other is long-wave IR for 8 to 12 micron. So you can use this quantum dot as an infrared photodetector. And actually, we have created that structure. So here is our basic structure for quantum dot infrared photodetector. We call it QDIP for short. So first, the 2.1 monolayer indium arsenide quantum dot is capped with indium gallium arsenide strain-leaf layer. Then it will be capped with gallium arsenide spacers. Here is the schematic diagram for the conduction band edge of this structure. So this deep potential represents a quantum dot, and this middle level represents this InGaAs strain-leaf layer, and this higher level is gallium arsenide spacers. So this structure will be repeated by n times. And on the edge of the structure, there is an gallium arsenide contact layer, which is separated by this doping setback layers. So in this structure, when the photon is impinging on this cubic structure, the electron inside the quantum dot will absorb the photon to be excited to the higher energy level, and this will extract it by fermionic emission or a tunnel, and it will be eventually collected as photocurrent, which is a signal for our qubit. So, and this energy separation needs to be tailored such that the detection wavelengths you desire to match this energy separation. So here, to improve the performance of your qubit, there are mainly two requirements. One is you need a large number of layers without too much of defect, because to have higher absorption. Actually, this is challenging because as I explained in the previous slide, the quantum dot itself is inherently strained. So during growing many number of layers, the strain will be accumulated, and it will be eventually defective. And another consideration is you need to optimize the electron occupancy in quantum dots such that the photocurrent is maximized while the current is minimized, which will give the maximum detectivity. This is a figure of merit of the qubit. So in this presentation, first I will show our progress to make low defect density of any number of layers, and then I will discuss about the semi-quantitative evaluation of the electron occupancy in our qubit structure. So here is the TM image of the qubit structure with a 10 period of qubit structure. These are cross-sectional TM images. This image is taken by Dr. Mahadingam at the Air Force Research Laboratory at Wright-Patterson. So in the area of the investigated, there is no indication of defect. And then we proceed to the 20 period of the qubit. And this is a cross-sectional TM image, and this is a prime view TM image of only the topmost layers. And even for 20 period, there is no indication of defect. And from this prime view image, we can estimate the quantum dot density as high as 4.5, 10 to the 10th per square centimeter, which is almost comparable to the quantum dot density at the first layers. So that indicates that there is no reduction of density. So the strain of the quantum dot is effectively accommodated by the combination of InGaAs strain leaf layer and the gallium arsenide spacer layers. So on this high quality structure qubit, we have measured its infrared photoresponse. So here is the photocurrent spectrum as a function of wavelength for 5-period qubit. As you can see, there is a nice peak around 8.5 micrometer, which is within the atmospheric optical window of the 8 to 12 micrometers. And this peak can be attributed to the transition between ground state to the mixture of quantum dot and quantum well states. And here is the photocurrent spectrum for 10-period qubit. It also shows the peak around between 8 to 12 micron, as well as these additional peaks, which will be discussed later. So next, I took those spectrum as a function of applied electric field, and we also measured the current as a function of electric field. So here one note is the photocurrent of the 10 period is less than 5 periods, in spite that we expect higher absorption. So from these results, it suggests that the doping did not give enough electron in 10 period qubit, therefore the electron occupancy in 10 period qubit is not good enough. Well, to investigate this electron population inside quantum dots, next we took the temperature-dependent current. The current can be simply described by the product of the electron density and electron charge and the velocity of electrons. And within these three parameters, electron density has a strong dependence of the temperature. So here is the Arrhenius plot of the current for 5 period qubit. So above 70 Kelvin, the log of the current linearly varies with inverse temperature. So from this temperature regime, we can calculate the activation energy of the qubit, which is plotted here. So interestingly, the activation energy of 10 period qubit is higher than this 5 period qubit, which suggests that this activation energy is not related to the quantum dot energies. And also, we note that the activation energy decreases with applied bias as much as about 40 or 70 millieV by 10 centimeter of the electric field. So now the question is, what does this activation energy represent in our qubit structure? To answer to this question, I'm going to consider about the possible source of the current in our qubit structure. So there are mainly three contributions of the current from the electrons inside quantum dots. One is this thermal emission from quantum dots, and the other is this thermal artist tunneling, which means that the thermally excited electron will tunnel through the barriers. And the third is sequential tunneling between adjacent quantum dot layers. And separate from the electrons inside quantum dots, there is also the possibility of the current emitting from the end-doped gallium arsenide layers. And within these four possibilities, only this thermal emission from contact layer can depend on activation energy, and this value will increase as a number of layers. So therefore, we conclude that the activation energy represents this energy separation between conduction band edge, the highest part of the conduction band edge, to the film energy. So now, if you know the ionization energy of quantum dots, you will know the energy level of the quantum dot with respect to film energy, and therefore you can estimate the electron occupancy inside the quantum dot. So to find that ionization energy of quantum dot, we took the photocurrent spectrum at various temperature and various biases. So from this spectrum, you can see there are mainly two peaks around this 8.5 micron and 5.5 microns. So for 8.5 micron peak, that's as we discussed before, this is the transition between the ground state of quantum dot to this mixture of quantum dot quantum wave state. And for this 5.5 micron peak, we note that its flow width at Hart maximum is about 100 millieV, which is almost comparable to that of interband photoluminescence, which implies that this 5.5 micron peak can be attributed to the transition between quantum dot ground states to the close to the conduction continuum state. So this value represents the ionization energy of quantum dot. So combined with the activation energy of the qubit structures, for 5-period qubit, the ground state of the quantum dot is much less than film energy. So all the quantum dot is occupied by electron. On the other hand, for the 10-period qubit, its activation energy is about 230 MeV, which is comparable to this ionization energy. So the middle quantum dot layer, ground state of middle quantum dot layer is almost close to the film energy. So it has a less electron compared to this 5-period qubits. So from these studies, the next thing we need to do is to optimize doping for when the number of layers is higher than 10 period. So first we have studied the impact of the spatial layer thickness on the occupancy of the electrons, occupancy of quantum dot by electrons. So by varying the doping spacer from 48 nanometer to 60 nanometer, which is from relatively small range, you can vary the photocurrent and the current by orders of magnitude. So for this highest, the qubit showing highest photocurrent, we also doped the gallium arsenide barrier in the multiple quantum dot region. So now the structure becomes NPN structure. So by doping the gallium arsenide region as much as about 2 times 10 to 16 per cubic centimeters, again the photocurrent and the current varies by orders of magnitude, which can be understood because of the higher acceptors, because of the higher acceptor density, which will raise the built-in potential in the multiple quantum dot structures. And so for another strategy to enhance the qubit structures, we are proposing to incorporate this our multiple quantum dot structure into the resonant cavity, in which the quantum dot region is resonantly sandwiched by 2 mirrors. And to avoid too thick layer of these mirrors, we propose this black mirror of combination of air and gallium arsenide by undercutting the sacrificial layer. So this is a demonstration of these bottom layers. And to incorporate this multiple quantum dot layer into the cavity structure, one needs sharp response of the qubit because of this narrow bandwidth for the cavity response. Then, so far we have demonstrated delta lambda over lambda is 15% in this mid-IR range. And the next work for us is to actually incorporate this qubit structure into the resonant cavity. Here is the conclusions and future work of my talk. Thank you for your attention.